let's continue with section 8.3b with more trig integrals. But this time, our trig integrals are going to involve secants and tangents. Yesterday, our integrals involved mostly sines and cosines. So now we'll have integral of tangent cubed x, secant cubed x dx. Alright, this particular type that I'm focusing on here are going to be ones that involve an odd power of tangents. So when you have an odd power or odd number of tangents, what we're going to do is separate out a tangent x, secant x. So in this case, we'll leave ourselves with a tangent squared, secant squared x, and have out here on the side a tangent x, secant x dx. Now this tangent x, secant x is going to be our du. So if du equals to tangent x, secant x, what do you think that means u is going to equal? Well, that's going to mean it's going to be a secant x. Now hopefully you guys notice that it won't matter whether or not secant is even or odd numbered here, because u will equal to our secant x. So if it happens to be an even powered of secants, then we'll just have an even number of u's. So we'll make this substitution. Now tangent squared is related to secant how? This is our Pythagorean identity. You need to know that tangent squared x is secant squared x minus 1. Some of you guys may remember that from the other day when you had to integrate a tangent squared. So if we think of it this way, then we'll have a u squared minus 1 times u squared du. So we can easily use the power rule. This is going to give us u to the fourth minus u squared du. So we've got 1/5 u to the fifth minus 1/3 u to the third plus c. Back substitute, and we'll be done. Alright, let's try tangent squared x secant to the fourth x dx. When we have ones here involving an even, this particular type is going to involve even power of secants. And when we have these, what we're going to do is break apart and separate out a secant squared x. So if you notice, with these last several examples that we've been doing today and yesterday, we have been trying to identify what du is, and basically working backwards to figure out what the u should be. Sometimes you're going to need to do that in order to figure out the problem. So in this case I have tangent squared, so that's a u squared, and then I have this secant squared x. Again, Pythagorean identity tells us that secant squared is tangent squared plus 1, so that gets plugged in. And then I have my du. So this is u to the fourth plus u squared du, which is 1/5 u to the fifth plus 1/3 u to the third plus c. And when we back substitute, it's just 1/5 tangent to the fifth x plus 1/3 tangent cubed x plus c. Alright, we've got 2 more to go. This time we're going to do one just with a tangent. Tangent cubed pi x dx. Well, hopefully you realize that we have to have Okay, this particular one's going to be a little bit different. We are going to break apart one tangent from 2 others. Because the trick here is that the derivative of tangent is secant squared, the derivative of secant is secant tangent, and we don't have a secant in here anywhere. So we're going to have to put one in there. So when I break this apart into two pieces, I have a tangent and a tangent squared, I end up replacing my tangent squared with the secant squared minus 1. Okay, try to remember, tangent squared theta plus 1 is secant squared theta. So if I want just tangent squared theta, it's secant squared minus 1. You do have to be careful here though, because I have a pi x, so that makes this secant squared pi x minus 1 dx. Now once we write it out like this, we're actually going to have to separate this into tangent pi x times secant squared pi x dx minus the integral of tangent pi x dx. We'll write it out as two separate ones. Hopefully you guys remember how to integrate this last one, the integral of a tangent. That should be easy, I'm hoping. But we're going to have to deal with this part. This is the trickier one. Okay, and there's a couple different ways to do this one. What do you guys think? What should we let u be, and what should du equal to? Well, so most of you guys will probably see that u equals to tangent pi x. Therefore, du will equal to pi secant squared pi x dx. Make sure you have that extra pi because that's from our chain rule. So 1 over pi equals to secant squared pi x dx. So plugging this in, we're going to have integral of 1 over pi times u du, which is 1 over 2 pi u squared, which is 1 over 2 pi tangent squared pi x. Now we still need to do this last part. Do you guys remember how to integrate a tangent pi x? If you don't, you might want to think of this as a sine pi x over cosine pi x, and then do a u substitution. Does that sound familiar? I'm hoping it is. I'm going to just jump right down to it. It's going to be 1 over pi natural log of cosine pi x, because the derivative of a cosine is a negative sign. Oh, and that makes this a plus, and then my plus c at the end. Okay. All right, very last example. Example 4. What about integrating a secant x over a tangent squared x dx? All right, we're going to think about this one a little bit differently. Let's try using some other trig functions in here. Because my tangent's on the bottom, the derivative of tangent is secant squared, so that doesn't quite work out. I'm going to try something else over here. I'm going to write this as a cotangent squared x dx, and then secants are 1 over cosines, cotangents are cosines over sines, and this can actually get rewritten as what? Let's see. Cancel out a cosine, so we have cosine x over sine squared x, and some of you guys may see that u could equal to sine x, so du will equal to a cosine x. Okay, so that is an option. I just want to show you one other way to do this, just to give you guys sort of a variety of different ways to do these. How about if I thought of this as a cotangent cosecant x dx? Because I have an extra sign on the bottom, so that's my cosecant. You guys remember the integral of a cotangent cosecant? That's going to be a negative cosecant x plus our constant.